Welcome to the first section where we're just going to take an overview of statistics, learn some vocabulary. And in fact, in the first few chapters, you're going to find we're doing a lot of vocabulary, just learning about the basic concepts and theories around statistics and statistical analysis. So the first question we have is, well, what is data? Statistics many times is the analyzation of data. So when we talk about data, we're talking about, information that comes from things we observe, counts that we make, measurements we make, or responses that we receive. So it's a pretty open thing. A lot of times data is made up of numbers, especially if they're counts or measurements. Other times data is made up of observations, what we observe occurring in a population. And a lot of times we're doing surveys and we're collecting responses. So just a couple of examples. According to a survey, more than 7 in 10 Americans, or 70% of Americans, say a nursing career is a prestigious occupation. So this statistic that we have collected here, if we're looking at the data was made up of a survey that was taken, and you could see this as being a kind of a yes or no. Would you consider a nursing career a prestigious occupation? And so in that survey that was collected, people would maybe say yes or no. If it's a phone, press 1 or press 2 for yes or no. So really our data set there would be considered a collection of yeses and nos to a response of this question. And in that survey, they found that 7 out of every 10 people, or 70%, said yes. But the data itself, in that case, would be made up of yeses and nos. Number 2, social media consumes kids' days as well as more score on their social media accounts at an average age of 11.4 years old. I think I'm going to try reading that again. Social media consumes kids today as well as more score on their first social media accounts at an average score of 11.4 years old. Okay, that was very awkwardly worded there, but basically they looked at the average age of kids who are using social media and found that the average age was about 11.4 years old. So here they collected a bunch of ages. So here our data would have been made up of ages of children. Statistics as a whole is the science of collecting, organizing, analyzing, and then interpreting data in order to make decisions. So there's a lot there to unpack, because when we talk about collecting, when we talk about science always wants to be extremely careful in every aspect of how it works. So there's a whole science behind, rules behind, theories behind the collection of data. And there's ways that we can organize it so we can begin to make sense of it. And then once we've organized it, we do some analysis on it. What is the data telling us? What are some numbers that we can get that would give us insight about this entire set of, say, 2,000 pieces of data? And then we have to interpret that, right? What does this tell us about the sample that we have taken? And hopefully, what does that tell us also about the larger population that our data was taken from? So already there, I've used a couple of words, population. So in a population, we can say, well, when we think of population, of course, you might think, oh, like the population of people within the United States. But that's okay, that is a population. But you could also get more specific. You could say the population of women within the United States, or you could say the population of men in Washington State, or a population could be the population of men who attend the university. So a population is really about however we first define it to be. It's kind of our target interest. If we're wanting to know about how men specifically feel in the state of Washington, then that would be our target, population. And so every man who is in the state of Washington would be part of that population. So it includes all possible outcomes, responses, measurements, or counts of that particular targeted population of interest. Now, of course, for most situations, populations are too large to reach. There's too many people within that population. We don't have the time, the money, the resources to try to find out a way to talk to all of them. And so instead of that, we will take a sample. And there's a whole science behind this as well, as we'll see. But basically, a sample would be a subset, a part of that population. So of this group of people, we randomly select 3 people to be their representatives. And so this would be a, sample of this larger population here. Population can be as small as a classroom of students, right? If I'm doing some analysis, my population could be the Math T110 students in my class at the University of Washington. And so that would be the population I have. Now, in that case, there's no reason for me to take a sample because I have access to all the information, right? I don't have to take a sample of 10 people to measure how people did on the last exam because I have all 30 or so student results. So in that case, I don't need to take a sample. But we can sometimes look at the results of samples within those smaller, more reachable populations to see how they behave. And in fact, that's really how we've we have built this entire theoretical and then backed up by mathematical evidence system of statistics. We've looked at how small populations, samples, behave in regards to their overall populations. Let's see if we can identify the population in the sample in this particular problem here. So in a recent survey, 834 employees in the United States were asked if they thought their jobs were highly stressful. Of the 834 respondents, 517 said yes. Identify the population and the sample, and then describe the sample data set. Okay, so when we look at this, we're being told about a survey that was conducted, and there was a bunch of people that were asked their opinion. And these are just employees in the United States. So they don't necessarily work for the government. They could work in the private sector, yada, yada, yada. So in the description here, we can see that the sample, how it was taken, represents the overall population we're hoping it will represent. Because basically we use samples to help give us an idea about large populations that the population itself, it's impossible for us to talk to everyone. And so in this case, our target population sounds like employees in the U.S. That is our target population, employees in the U.S. Now, the sample that we took consists of these 834 employees, right? These people that we talked to and collected information from, we're hoping will give us an idea of how the overall population of all employees in the United States feel. And so we use this sample result to get us an idea. And so one thing we could collect from this is 517 said they thought their jobs were highly stressful. So 517 out of 834, whatever percentage that came in, that's the percent of our sample that said yes. And so we assume that the overall population is probably not exactly the same as that percentage, but is probably close to that, right? We assume that this sample will represent the larger population. So just to summarize here, the population consists of all employees in the U.S. The sample consisted of the 834 employees that took the survey. The sample is a subset of all U.S. employees, and the data consisted of 517 yeses and 317 nos. So that's that's what we collected. So our data was literally, in this case, a bunch of yeses and a bunch of nos. So we have all employees, population in the U.S. We'd probably be more specific there, just say the U.S. because there's employees outside of the U.S. And then the employees in the survey, that's our sample. This is just a small circle within a larger population. We tend to think of all the numbers that we hear all the time as being, these numbers are statistics, right? They're describing, so these are numbers that describe things, people, places, and things. And yeah, that's kind of true. But in mathematics, we have a very specific definition. In fact, there's two different types of numbers that we generally see. One is called a parameter, and the other is called a statistic. And there is a difference between those. Mainly the difference is the source of the number that we're discussing. For a parameter is a numerical description of a populational characteristic. So, for example, the average age of all people in the United States. So that would be our population parameter. You'll notice P and P, they go together. That's just one way to remember. So most populations, like here if we're talking about average age of everybody in the U.S., that's kind of a difficult number that would be a different number to come up with. As simple as that idea is, we don't really know what that number is, and it would be really difficult for us to try to figure it out. So that would be a population parameter. Now, I could call my target population average age of students in my classroom, and let's say the average age was, 30. So that number of 30, that average age of 30, would be a parameter, not a statistic, a parameter. Because I took everybody who's in my classroom, we wrote down their age, we calculated that number, and that number represents a number that was derived or had its source with the entire population of the classroom, right? So it's all about what is our target population. If a number comes from a sample, then that is a statistic. Okay, so statistics are specifically numbers that we derive from samples that we've taken from larger populations. So if we were to find the average age of people from a sample of 3 different states, that would be a statistic. They were collected from a sample. Okay, so here if we're going to distinguish between a population parameter and a statistic, we're going to read each one of these and kind of decide. So decide whether each number describes a population parameter or a sample statistic. A survey of several hundred collegiate student athletes in the United States found that during the season of their sport, the average time spent on athletics by student athletes is 50 hours per week. Let's read that once again. A survey of several hundred collegiate student athletes in the U.S. found that during the season of their sport, the average time spent on athletics by student athletes is 50 hours per week. So is that a population parameter or a sample statistic? We have to think about, where did this number 50 come from? And we're told that the survey came from several hundred collegiate student athletes in the U.S. So several hundred obviously does not represent all athletes in the U.S., even though we use that number to try to describe, on average, how these students, we sort of projected it onto all student athletes in the U.S., right? Just to get an average. But this would be a sample statistic, because it had its source at a sample, a survey of several hundred collegiate student athletes. That would be a sample, and hence a statistic. Second one, a freshman class at a university has an average SAT math score of 514. Okay, so in this case, we have to think about what is the target population here. The target population is just the freshman class at this university. And this is something that they could actually probably figure out, right? SAT scores tend to be things that schools, they're in their database, possibly. And so this would be something where we could actually get every freshman student's SAT score. And so this would be a parameter, a population parameter. Why? Because we're not trying to describe the average SAT scores of all students in the U.S., simply the average SAT score of students in this freshman class at this particular university. And so that's a reachable population. And the way it is worded, it made it sound like they took everything into consideration. Now, if they went into further detail and maybe they didn't want to have to go through all that, maybe they did a survey, but that was not described in this particular wording. Let's try another one. In a random check of several hundred retail stores, the Food and Drug Administration found that 35% of the stores were not storing fish at the proper temperature. Oh, God. So, yeah, okay. Storing fish at the proper temperature, I underlined that, but that's really the variable here in this situation. It's like that's what they're trying to figure out. Were they the correct or non-correct temperature? But random check of several hundred retail stores. Okay, well, that doesn't sound like, nor would it be realistic to expect that they went to every single store that has fish. But in this sample that we took of several hundred retail stores, we came up with this value here, 34%. This is a sample statistic. As we begin here, when we're talking about statistics, we sometimes will divide them up into two different areas. But of course, they all overlap with each other. But there's statistics that we're used to seeing, which we call descriptive statistics. And then we have the more advanced stuff, which is inferential statistics. So in descriptive statistics, which was what we're really going to be focusing on here at the beginning, descriptive statistics involves organizing, summarizing, and then displaying data. So all of those have their bits and pieces that we're going to look at. How do we organize data in a reliable and financially reasonable way? How do we summarize it? What are the options that we have for summarizing, and what are some ways we can display it? I like to think of descriptive statistics as the hard numbers. These are not things that could be argued about. These are just the same things, and they just reflect the underlying data. So descriptive statistics tends to be stuff that's like the hard numbers. Like if you're to, sports statistics, when they look at the RBIs and the number of touchdowns a team has had, or all those different numbers that we look at, those are descriptions simply of data that they've collected throughout the year. And when we look at inferential statistics, this is when we collect samples and we use those samples to draw conclusions about the larger population from whence those samples came. That's when we are making an inference about a larger population. And there's a whole science behind the inferences that we're making. We're not just making conclusions off the top of our head, our opinions, what we think. We're looking at the data we've collected, and if the data is reliable, so it was collected in a good way, it wasn't biased, and we used some techniques, and we'll look at all the different little techniques we would want to use. But from that data, assuming it is representative of the population, we can make pretty reliable predictions or observations about the larger populations. All right, here we're going to identify first the population and then the sample. And then we determine which part of the study represents the descriptive branch of the stats, and what conclusions might be drawn from the study using inferential statistics. All right, so a study found that 2,560 U.S. adults found that adults not using the internet, 23% are from households earning $30,000 annually, as shown in the figure. So here we have not online. Who's not online? So we have U.S. adults who don't use the internet. 23% have less than $30,000 in income. 12%, 30 to 49. Only 6% of people from 50,000 to 75,000 don't use the internet, and 3% of the people who make 75,000 or more don't have access to the internet or don't use it. Okay, so first of all, what is our population here? Well, we want to look at who did they survey, right? And so when we talk about the population, it sounds like it's just U.S. adults, right? That's all they really said, U.S. adults. So our target population here was U.S. adults, and the sample is the 2,560 U.S. adults that they talked to. So this would be the sample in this problem. Population, U.S. adults, sample is specifically the 2,560 adults that they talked to. Okay. Which represents the descriptive part of statistics. Well, in this case, the results of our survey found this number here. So 23% from households earning less than $30,000 annually. That's the descriptive, right? That's what we discovered. These are the numbers that we calculated from our sample. The inferential part of this would be for us to apply this to all U.S. adults, right? So if we wanted to apply this to a larger population, we could say probably, somewhere around 23% of all households earning less than $30,000 do not have access to the internet. Now, we can actually get more specific than that, okay? We can actually say, well, we think it's from here to here. So we get an idea of what our margin of error is based on the size of my sample and other things. So we can get an idea of how far we think that number 23%, this 23% only represents, right, the 2,560. That's the result we got from those. But if we want to apply it further, let's say there was a 2% margin of error, we would say anywhere from 21, 2% less than 23, up to 25%, 2% more than 23, of households that earn less than $30,000 annually do not have access to the internet. That would be a type of inferential conclusion that we could draw from this, possibly. Looking at one more example, a study of 300 Wall Street analysts found that the percent who incorrectly forecasted high-tech earnings in a recent year was 44%. All right, so here our target population here is Wall Street analysts, and the sample is the 300 Wall Street analysts that we talked to. So this is our sample, this is our population. We want to find out some information about the Wall Street analysts, so we take a small sample of them. The descriptive statistic, of course, is the 44%. That's describing the sample result that we took. And if we were to draw a conclusion about that, we would say that somewhere around this number of 44% represents the entire population of Wall Street analysts. That would be the conclusion I could draw here, assuming that this was a good sample. Again, it's not going to be equal to 44%, because that just represents the 300 that they talked to. But we believe it'll be somewhere within that range, somewhere around 44%.